Right. Well, I guess we were talking about mass spectrometry. I hope that sounds familiar. Okay. Well, good. Um, I did do some changing on this. So the second half isn't going to, if you have the presentation from what I started on before, I kind of stopped at slide 47 and it's new from then on. So the recorded version will be correct and complete, but the you've been sent isn't complete or correct. So what we were doing, looking at mass spectrometry, different applications of it. And one of the places where we find it, again, good deal of use is measuring, quantifying some things. And that's actually a fairly simple task you use to use in an isotope. So a stable isotope. So instead of carbon 12, it's carbon 13, or a different isotope. So we have exactly the same compound in terms of chemical characteristics. It's the same volatility, the label, the heavier carbon sample versus the regular carbon sample. They chemically react, they extract the volatility, whatever steps you do in cleanup, they behave the same way. So to put an internal standard in, that's exactly the same compound, except for one carbon, being carbon 13. It's a marvelous way to actually do any kind of quantification. So you decide what you want to measure. You need to find, of course, a carbon 13 labeled sample of that. It's not radioactive, it's a stable isotope. So you can then go ahead and add it, and I'll give an example of that. You can do MS, where you then simply model or measure the compound of interest. You can take the most abundant peak of that compound of interest and measure it. At the same time, you do exactly the same for one mass heavier. And so you get exactly the rate you want. And plot ions of interest, integrate as you would a regular peak, and basically use proportions. So I got an example of that if it makes a little more sense. This isn't a compound that we're particularly interested in, 5-fluorouracil in blood plasma is what's measured. This is the compound here, and this has a mass that's 158. There's two nitrogens in here, and they're nitrogen 15. So we're somewhere along here. And so this is the unlabeled compound, and this is the labeled standard. So it's measuring that 5-fluorouracil. It has a label in it, known concentration in your sample, extraction, and comparing it in peak area to the sample of interest. So, like I say, you always look for an internal standard. You want to quantify anything, you have to have some benchmark. It has something to anchor it against. And so often we choose another compound, not the same compound. We want to measure, benzaldehyde. We could use almost any other compound. And okay, that works as long as, we get separation measured. If you can use exactly the same compound, then it's really good quantitative data. So basically, using mass spectrometry to be that selective is a tremendous help in terms of accuracy and quantitation. Purity of a GC peak is if you're doing LC, you're doing gas chromatography, you're doing any kind of chromatography, and if you get a peak, it looks nice, it's beautiful, symmetry, whatever. Do you know that it's one compound? No, you really don't. You don't unless you get a mass spectrum of it. You can then take mass spectra across that peak and see if it changes in any way, that there's some other compound is present. If there's several computer choices for an identity, which is correct, and that's what a good deal of activity that's going on right now is, of course, looking at all the plant proteins, looking at the off-flavor components in the protein isolates, look at the profile of the plant material it starts from, go through processing, and then look at how your chemical profile of aroma compounds, volatile compounds, has changed. And so you're going to be doing studies where you try to isolate all the volatiles and then look at the quantitative data on those volatiles, how they change as processing. But do you only get one choice when you do an identity? So you get a nice spectrum. but does it know the right compound? Has it picked the right compound for you? And so that's one place where MS works pretty nicely. So you're actually doing a mass spectrum. So you get this kind of a spectrum off a compound. And then you'll pick one ion. When you say, I want to know exactly what this is. I want to know what this ion is, or this ion, this ion, this ion. And so you actually do one mass spec gives you an ion profile, and then you do a second one to authenticate what exactly are those individual pieces. So again, it's a very powerful way of confirming identity or being sure that you know what you're measuring. And what we find is that the mass spectrometer that does that kind of thing, does a double mass spectrum measurement, is called a triple quad mass spectrometer. Today's choice for quantitative analysis. Then again, you know exactly what you're measuring. It has sensitivity, specificity, unfortunately, a pretty good price tag. You're lucky to get them for around $250,000 and more. So it's an expensive piece of equipment, but again, it does certain things for you. And so, there's lots of options on this. I think that's good for analytical problems. And kind of what I mentioned about the problem right now, looking at volatile compounds, identifying them and quantifying them in plant proteins or any other, I don't care, any other product. Maybe you're working on meat, what flavor compounds are in meat. Okay, good. So this technique is extremely valuable for that. And this particular problem that I'm giving you an example of comes from one of your colleagues. So Chrissy is doing a project down in food science, obviously, grad student there. And she's looking at a soy base before and after texturizing. At least she didn't tell me too much. How's that? That's what I think it is. So she was doing a purge and trap for a vault to collect volatiles from her product. And purge and trap is nothing more than taking your sample. If it's a solid, grind it up, add some water to it. So you've got an aqueous slurry of your product and water. Then you bubble an inert gas through it. So nitrogen gas going through this sample. And that nitrogen gas will collect some of the volatiles. Some of the volatiles will partition into that gas that you're bubbling through the sample. So your exit gas, is loaded with some volatiles. You pass that stream through a trapping material that absorbs your flavor compounds, and you just kind of load them up and trap them here. Then you take that out, put it into a gas chromatograph, and empty that into your gas chromatographic column or gas chromatographic instruments. And that's then attached to an MS, so you can get mass spectra of the volatile compounds that you're looking at. So this again is from Chrissy Stated. And so this is just one section of it, one of the treatments and so on. These are the compounds, at least I think it was just 20 or 24 compounds that were identified. And they're in elution order. So they're the solute first level gas, second, third, fourth, fifth, and so on, down the line. So you have a chromatogram. Of course, you see here comes one peak, here comes two, here comes 3 and 4, 5, and so on. So you get them coming out and drawing as chromatogram. And so the information that you get is this is what the mass spec says. This is probably it. So this compound came out at 3.202 minutes. Stronger, GC, I should say, is more like metogamy. That could be certainly a contaminant as opposed to a flavor compound. And so you get a match or a guess from the computer. How's that? And so it gives you detention time. And we could go time since I pointed it out. Here's one sample, here's 11 pictures of that sample. And the computer then picks the compound for you. And it says how good is its guess. Runs from 0 to 100. 0, you don't ever see, but you don't see 100 either. It goes right down to it. And so basically the computer says we got 90% match, 93% match. Okay, you feel pretty good about that. And you also get from mass spectrometer some kind of area under the curve. So if you're looking for some rough quantification, that's useful. So it'll spit out data like this for 50 compounds, 100 compounds, 150, whatever that you get in your gas chromatographic run. When you start then looking at the data, the first thing you say, wait a minute, these gases that you've given me up here, they're based on mass spectra. Okay, so that's one data point, one basically way to look at the compound. And okay, we got our matches coming across. But a good mass spectrum is not absolute identification. This is a low resolution instrument. Mass 94, for example, can come from different combinations. Looks like the right match, could be the right match, but it's not absolutely good enough to say it is what it is. And if you're going to publish this, you're going to be darn certain that it is what you say. If you don't know, sometimes no matter what you do, you don't know. You can list it as tentative, right? But okay, you differentiate what you know and what you don't. The next positive bit of data that you need are retention indices. Retention indices are basically, let me see if I can draw this in a way, I suppose, that Chrissy isn't going to see because she's watching it on. But so what you would do, this is a nice temperature program to run on the JC. You get time on that way, and you get intensity here. So intensity, this would be, for example, let's see, 7 hydrocarbons, the 8 hydrocarbon. Oops, is that backwards? And so what you do is you spike your sample with hydrocarbons, a complete set of hydrocarbons that may run from C6 all the way out to C22, 23. And so you have hydrocarbons as benchmarks. And so you actually put the hydrocarbons into your sample. And so this may be something from your sample. I mean, there's going to be lots of, let's say, of interest. Well, we've got a benchmark in here. We know that this compound, unknown compound, is going to elute between the 7 carbon and 8 carbon hydrocarbons. And so you actually give that a number when you calculate and interpolate. And let's say that's 730. It's the 7th hydrocarbon. It's about 30% of the way there. And so this is a retention index. And so that is exceedingly useful. And that's what I've added on to the table sand. So the various peaks run through this particular compound, which is 2-methylpurane, as it says over there, elutes between the 8th and 9th hydrocarbons 62% along the way. It's basically pinning down where that elutes between hydrocarbons. That's used globally. That is the standard method of pinning down where something elutes across the globe analytically. And so those numbers are published from other people's works. You see what in literature, and you can get some numbers from the literature. So it translates what you do here to what somebody does in China and somebody does any place else in the world. And so you take a look at the numbers from literature, so 876, that's 862. I'd like to see them no more than 10 different. Because it is a different machine. It is in a different country. It is in a different place. Different column. Well, it's the same column, but maybe different temperature band or so on. So there's some variables that are different. So you leave a little bit of leeway here, but that's about 14. And I'd rather say, well, that's kind of the place where it raises a question to me. I don't know about that. I'm not comfortable with it yet. This one here is within 12 of buckle 10. That's about my limit on it. And so maybe I'm okay over there, but look at the match here. So to match this one, 87% matches. pretty good. I like to see 90%. But I got a 64%. That's not a good match. This is 47% match by the MS 40. That's not very good at all. And so I kind of highlighted in red those I had question about. So this is all about the mass spec tells you. And then you start saying, well, am I comfortable with? And all of these in red, I'm not comfortable with. I mean, they're wrong. But it means that I'm going to give them some extra time, some extra effort to ensure they are close. I said they are. And if I don't know if they are, okay, you let them know. No. Got 2 ethyl furan, so on online published literature. So all of these are black, fine, they're good, no problem at all. I've got retention indices, I have mass spectral data, I have an identification. But anything in red, you start saying, I want to look more into what has happened to that, or look, is that identity correct? And so one way, or the next step then, for those that you kind of wonder about, you get spectrum of questionable identity. So how many, 5, 9, whatever it was on the last slide, I would be going to literature. And so here's what I got in my machine for a mass spectrum. Let me pick up something from the literature. Believe me, these things are available, which is really interesting. Available from many sources. So you pick out a spectrum and you start looking at it yourself. Okay, the machine like that. Do I like that? And so you start looking in that direction. Compare the unknown spectra to a known reference material. And so I'll show you an example of that. So this again comes from Christy Standard. She's saying, I wasn't sure about this particular compound. She got this in her analysis, analytical run. This compound fragmented into a piece that had a mass of 32. Another piece of that molecule had a mass of 39, 45, 51, 56, and so on. And so that is a typical mass spectrum of the pieces it was blown into within the mass spectrometer. So that's the unknown. And she kind of got 2 choices for this. The mass spectrometer liked 2-vinylfuran as a choice. But that was interesting because in one sample it liked the 2-vinylfuran, another one it liked that methyl disulfide. You know, it's kind of the same compound eluting in about the same place. And so we have a schizophrenic mass spectrometer, the spectrum a little different. And so this is one compound that was picked up for this unknown peak, and this is the second one. Then you start looking at the 2. There's really some nice books on this, you know, something like reading for evening, whatever, that tell you how to interpret these, how to know molecules, weak bonds, where they break. I mean, a good chemist will sit down and say, oh, I know that fragment, I know that piece, that's logical, so on. I don't have that knowledge or skill at all. I have to look and say, looks like a good fit, it doesn't look like a good fit. And so when we look at this unknown, 2-vinylfuran, if that's correct, it should have a piece of, at 79. So you're unknown to something at 79, there's no 79. And so that molecule is not going to have a fragment here. Literature, no, there's no pieces here. This unknown has a piece here. So it can't be the 2-vinylfuran. It might be a mixture of something. That's what I'm leaning towards. But we look down here at dimethyl sulfide, which actually have similar retention indices by gas chromatography too. So curses, I can't look at the GC run and say, oh, that thing came off here, that's that, and that came off here. It's the molecules are actually very, very similar, even though they wouldn't think so. And so I kind of look at that 79, and there is a 79 here. So I'm reading this, there definitely is dimethyl sulfide here. I've got the right pieces for it. 45 is a little smaller, 79 is a little smaller, that's bigger. So it doesn't exactly match this, but there's no way it can be that, at least in its entirety. And so, in my opinion, we've got probably a mixture of the 2, because that's would account for the 79. This 45 down here will contribute this. So if you put the 2 together, you have a 65 goes in here. 39 that fills in here, 45 again. You actually get your spectrum here if you put these two together in some combination of amounts. And so what would you do about that? Well, wait a minute, I'll come to that in a moment. One other sample that was a similar question I'm not as lucky at in terms of picking out a good solution. It's one of our other compounds. It's an unknown that moves very early. One of the choices was pentanal, and the other choice was 2-methylbutanol. And so this is a 5-carbon aldehyde, that's a 5-carbon aldehyde. The only difference is, of course, you got a methyl group hanging off, where that's a linear chain. But if you look at the unknown, we got a mass molecular weight. This is a paired compound, will not be composed at all. 86, 86, that looks really good. 71, well, we don't have much in 71, but we have a little 71. The 71 looks better here. That 71 is about the same as here. So pentanal looks like a better fit here than the 2-methylbutanol. 58, 58, 58, 44, 44, and that's 43, 44. And so again, you do this kind of looking and say, what's my best choice for this whole thing? So like I said, I'd rather see a little more 71 comfortable here, but it's leaning towards the 2-methylbutanol. So, oh good, you're leaning towards that. Do you put that in your publication? I don't know for sure what this is, but I'm kind of leaning towards that. They don't, readers don't like that approach. And so what the next step on this, how do I know exactly what it is? I would get the pure chemicals and look for the exact chromatography. So it's really unusual that two compounds will have exactly the same elution time. But we're comparing our elution time to the literature. We say it's good. Well, that literature has a pretty big window. The literature doesn't really differentiate between the retention of these two compounds. And so the best way to do it is to get the two compounds, get your sample, and then go ahead and get retention data on that. Because the gas chromatography is really good in terms of resolution. You start using that, you can determine or separate most compounds using that technology. So again, I would look for co-chromatography on my system, the same system I got in that spectrum, and look for identification based on that. But I guess certainly my point is that you have to be careful. And again, I've said that many times. Machines put out numbers, they don't tell you which one's correct. And unless you kind of know some of this, what can you do about it? Can you improve your guess? Can you improve, how do you do that? And of course, the first thing you say is how important is it to you? And then you start putting some work into it. But there's not a simple way to resolve that, other than, like I say, doing your best chromatography, looking for a slight shift in peaks between the two compounds, the two tentative identifications. And you will more than likely get a separation at that point. So not simple. It's a lot easier to publish a list of things than it is to actually get into it and try to determine what these compounds are. And again, a lot of people don't do that. And your data then oftentimes are certainly flawed to get in literature. What I wanted to do is spend the rest of the time today going over some applications in foods of mass spectrometry. You've kind of got an idea of what hardware is there, what parts are, the ion source. You have some means of separating these ions, so you can count the ions and how big are they. And okay, so we have detectors and so on. There's always some interest in how you get a sample into a mass spectrometer. Gas chromatography, liquid chromatography are most convenient ways to get samples in. But again, there's other approaches as well. So let's kind of look at some applications. Once you know, I put flavor protein reactions on top, a little prejudice, since that's what we do. So flavor protein reactions, there's interesting. There's a lot of work that's been done on how flavors get released from foods when they're in your mouth. The Vermin Symposium that's been in the German in Germany since maybe 1960 or so. And every 3 years, this conference goes on. It's the best people around the world participating in basically flavor analysis, flavor blurring. And so this has been a topic, and I don't know if I mentioned it or not, I hope not, but the topic in the last one, which would happen this spring, was how flavors are changed in the mouth. Now that one drives you a little bit crazy. So there's a compound in the food. That compound gets in your mouth, it changes to another one by the enzymes in the mouth. And so what you perceive is not the character of the chemical that you're consuming. Does that make it a little harder to figure out what causes? Yes, it does. So this whole idea of aroma release in the mouth, and then how that aroma may be all altered is I guess I'd call that a hot topic today also. We had 3 full days of lectures from around the world talking about that particular assumption. But I'm going to go on a very simple one, give a simple example. We go through examples of each of these. Identification of unknowns in the food, I think we just spent some time on that. The surety of purity. So when we buy something, we make something, is it pure? Is it only? For example here. Quantification, a little bit of quantifying work. Adulteration, something that shouldn't be there. So we'll give a little bit of examples of these and give appreciation for how it might be used. The idea of flavor reactions with proteins. The first thing that I guess comes to mind is that if you put a flavor in contact with a protein, there's going to be a reaction. How many amino acids are there? What functional groups are there? There's acids, right? If you look at the side chains, we got acids, aspartic acid, glutamic acid. We have alcohols, serine, threonine. We have amines, arginine, histidine, lysine. We've got alcohols from serine, threonine. Oh, did I say that already? Anyway, we have a beautiful group of functional compounds that are available for chemical reaction. And so when we put our flavor compounds in there, they're also functional. They will chemically react. The Maillard reaction reacts with the epsilon group of lysine very readily. You can also get that same reaction with cherry flavor or many compounds that are used in flavoring. So we put our flavor into a high protein food, well, any protein food, but the higher the protein content is, the greater this problem becomes. We're going to get parts of our flavor. Anything that will react with those side chain groups are going to be disappeared. They're going to be covalently bonded. They're not going to make a contribution to flavor. In some cases, that can destroy the flavor, it just disappears because you've got the key components that are disappearing. And sometimes it just changes. We took all the aldehydes out of my flavor, left me with garbage. And so the idea of loss of flavor certainly is one issue. An undesirable change in flavor is interesting too. One that I kind of added on to this list I think is interesting, and that's the influence of this whole reaction on shelf life of a product. When the product reaches the end of shelf life, what's the most common reason? Has the vitamin C fallen too low, perhaps? Has the protein been reduced in nutritional value? Maybe. But the consumer doesn't know that. What the consumer knows is this doesn't taste good. And so what happens? We have an end of shelf life. The faster that flavor is reacting with your protein, the shorter your end of shelf life. How many years have we been adding antioxidants to foods? How many years have we been putting it in packaging that's oxygen impermeable? How many years have we been working towards limiting oxidation? When maybe oxidation isn't the only problem. Maybe we wouldn't have to worry so much about oxidation if we could keep a good flavor. So are we getting a short shelf life? Unnecessarily, because we're not protecting the desirable flavor of the product. So that's an interesting one to me. So how do we measure flavor protein reactions? Wouldn't you know, by mass spectrometry. And so this is beta-lactoglobulin. Why beta-lactoglobulin? I like it because it's a small protein, 18,276 for this period. And so if you do ESI mass spectrometry, electrospray ionization mass spectrometry, this is the scan that you get when we get our components. There's beta-lactic globulin. There's some oxidation of that protein, so we got smaller additions onto here. Once you know, lactose will add on. We get some browning. We produce a little bit of lactose added on to our protein, maybe one lactose, maybe two lactoses. But our mass spectrometer says, here's a protein, here's some oxidation products, here's your first lactose or second. We can count the number of lactoses being added on for browning. So that's really nice. Now, maybe I take that same protein and I go ahead. And so this is the same mass spectrum. It's now half of it instead of the whole one. This is half it shrunk. Well, beta-lactic globulin, lactose added 2 lactoses. Here's where one of my PhD students added benzaldehyde, cherry flavor to it. And that's a very low level. And all of a sudden, what do we say? It doesn't say 10 minutes. Okay, 10 minutes after adding it, he takes the mass spectrum of that protein. 10 minutes later, there's actually covalently bonded benzaldehyde adding onto my protein, covalently adding on to my protein with lactose. Within 10 minutes, you can see that the flavor is being consumed. This is 6 hours later. Now, this unreacted pure beta-lactic globulin, almost equal, almost 50% of the protein has had at least one benzaldehyde added on. And the same here. So your flavor is disappearing as it goes on. So in a really nice way to look at protein flavor reactions. Problem is, of course, you guys working with plant protein ruins my day because I can't do any masses that large. Beta-lactic globulin is perfect for that mass spectrometer. It's not perfect, for plant proteins. And so that's where we get stuck with it. Now we're using carbon-14 labeled flavor compounds. So we take our flavor solution, add a C14 labeled cherry flavor to it, shake it up, allow it to sit like the time we want, then take our sample, extract out the free, unbound flavor compound, and then count radioactivity of our protein. And so we look at radioactivity in the protein. But it was much easier when you could just put it in a little vial and run it through the LCMS. This is a big neck. Different example, determine the effect of replacing a bulk sweetener sucrose with aspartame on aroma release profile. Is a sugar sweetened beverage the same as an aspartame, a high intensity sweetened beverage? Do you get the same flavor profile out of it? Not really. Changes the flavor profile a lot, whether using a bulk sweetener or a high intensity sweetener. And so this is, again, place for mass spectrometry. 3 different samples were prepared. One was a beverage flavor with no sweetener. One was sweetened with aspartame. One was sweetened with sucrose. And so prepared a beverage base, 200 parts per million flavor, and then did some analysis. And that's a friend in the United Kingdom. So he's having his sugar sweetened, aspartame sweetened, whatever beverage, and he's sucking into his mouth. And there's always an exhale breath. I imagine you all sit and think about that every time you swallow. Every time you swallow, you exhale. Okay, so that's the first shot. You swallow, the food goes down your windpipe. As soon as you swallow, you exhale. That air goes right past everything you just swallowed and comes out your nose. So there's an exhale breath. And then each subsequent breath, it's the same kind of thing. You breathe in, you breathe out. So any residual beverage and residual food in there, you get to smell like you're in. And so here we have our mass spectrometer connected, going up his nose. So he takes it in, he swallows, and he breathes, and then he monitors the flavor compounds. Are they released? And this is much more complicated than it is. This is him sitting there, and this is minutes. So he didn't have the beverage. Didn't have beverage. This is acetone in your breath. We exhale acid. So the machine is keeping track. You inhale, the signal drops off because you're drawing lab air in. Exhale, it's across the food that you swallow. So inhale, exhale, so on, coming across. And then this is one flavor compound in the mixture, second, third, fourth, the fifth, the sixth. So 6 different flavor compounds within that beverage. And you'll notice it's called the exhale breath, the first one. There's a good shot of one of the flavor molecules in that first breath, and then it declines very rapidly. This another flavor compound, very similar pattern. Actually, all 4 of these volatile compounds are very similar. And when you look at their composition, they are chemically related compounds. But these 2 down here are much heavier, much less volatile. They don't all come out immediately. You get a little bulk, and then okay, a little more, and this tails on. This is aftertaste. So what you sense after you swallow it, your bright, fresh flavor compounds have gone away. They're no longer in your system unless you swallow again with some orange juice. So you can kind of get an idea of what flavor molecules are released and which ones are retained. You can change the formulation and look and say, how do I change the stimulus that the person's been given? It's a rather interesting one. Peak purity, well, okay, we know that one. GC MS, you look at the MS. Adulteration, certainly is it all natural? There's nothing better than mass spectrometry to look for artificial sweeteners being used, chemicals that are not natural or considered natural. And oftentimes the ability to take exactly the same chemical that was synthesized in the lab and that same chemical is synthesized by a plant and differentiate and say, did that flavor compound, was that, coming from organic synthesis or coming from the plant itself? Undesirable components, a great technique as you'd expect for pesticides, contaminants, off flavors, so on down the line. One thing that we've been dabbling with is imaging by mass spectrometry. I'm interested in encapsulation. I'm interested in protecting a flavor. I want to put in some kind of a shell, some kind of a particle. And that particle is here. But I don't know where my flavor is. It should be in here somewhere. I'm not quite sure how this is partitioned. Is this particle, my capsule, is it uniform across here? So I don't know a lot about that structure. And that structure is my barrier. It's my barrier to protection. It keeps oxygen from coming in. So I'm really interested in this wall material, the shell material, because that is my oxygen barrier to keep it from destroying the flavor. So again, how can you look at the structure, how it partitions during processing and formation by using mass spectrometry? So I'm basically using scanning by bombarding every part of this process and looking at the chemical composition of the barrier that's been presented. Quantitation, identification, well, qualitative. Identification of unknowns, that's a pain in the butt. It's a problem just because of the number of compounds you're looking at. When we look at flavors, well over 10,000 aroma compounds have been found in nature. They've been identified. And where do you start on a mess like that to try and straighten out what's there, what should, proper identification and so on? It's an exceedingly challenging area. Giving you an example of what Chrissy was doing. And you get exactly not just one of those or 2 of those that look like that. You get many of those problems where, gosh, it could be that, it could be that. And then it's really different, whether it's that or that. And so it's an extremely challenging area. I'm interested in what makes a food taste like it does. And of course, what makes a food taste bad. And that's really a difficult challenge. It's tough to make that link between analytical and perception, what the brain does. It's certainly a growing technique. Mass spectrometry is a growing technique in the food field. At one time, mass spectrometry was exceedingly expensive. For my doctorate degree, I ran a mass spectrometer for 3 years. That was my job at the university while as a grad student, is looking after all mass spectrometry. And we only had one. Okay, so that wasn't so many instruments. but they were so expensive, they're so limited. Now that they're kind of a dime a dozen, or kind of the workhorse mass spectrometer. So costs has come down. They're easy to operate, not maybe to interpret what you get, but they're easy to operate. You can push a button, you get all kinds of data. We've got wonderfully computerized databases on so many compounds, so the searching gets to be easy. Data handling, again, gets easier and easier. And advances in instrumentation and so on down the line. It's exceedingly useful technique. And you're going to find it more and more routinely. Even a smaller company may end up having a mass spectrometer just because the cost has come down and they're so valuable to a company. So I think that should be end of presentation. I think I'm 10 minutes early. You can either go home or you can stay and sit if you want. I'm teasing you, obviously. I think we're done unless you have any questions. If you have any questions, happy to answer them. If you got any questions about what you're doing, what flavors, I can help. I think you know where I am down in food science. So stop in. Anyway, have a good day.